All right, this is the second last, not the last, the second last lesson on this motion topic. So we started with work in lesson 20. Now in lesson 21 we'll move on to energy. All right, so when we do work, such as pushing a wheelbarrow, what you will notice is that you get tired. All right, so when you get tired, you use up what we call energy. In everyday life, we talk about, oh, I've got no energy and all that sort of thing. So in the physics terms, energy is the ability to do work. So in every day, oh, I'm tired, I'm lacking energy. Okay, so the ability to do work. Now, energy doesn't just disappear. One of two things. Sometimes it might appear that it disappears, but one of two things happens. First of all, it can transfer to another object, or the other thing it can do is transform into another kind. All right, and we've seen already plenty of examples of things which transform. So we did electric circuits, so electrical energy can transform into light energy, even sound energy it can transform into, and so on. All right, so they're the two main things that we need to remember about energy. Well, three main things, I guess. Well, no, two in that it's the ability to do work and it doesn't disappear. So in the second one, there's two parts. It either gets transferred to another object or transformed into something else. So this leads to what we would formulate as the principle of conservation of energy. So conservation of energy and conservation of energy says energy is neither created or destroyed. All right, so energy is neither created nor destroyed. All right, so as it said, the energy has got to go either be transformed to another object or transferred to another object or transformed to another kind. So in your notes there it says we say that work done by an object. So if it's done by an object, then what we have is transfer from that object. And if it's done on, what we have is a gain in energy for that object. Or you could also think, if you're talking about the transfer to would be another way of looking at that. So one way we can think about that then is, and people always forget this, so I'm going to write it big, that work is change in energy. All right, so work and energy are linked. If there's work done, there'll be a change of some sort of energy, and vice versa. If there's a change of some sort of energy, then there's work done. Now, work has the unit joule, and so energy also has, if work is change in energy, that's joule also. All right, so same units for work and energy, both joule. All right, so the example in there, so it says the man does 200 joule of work pushing a wheelbarrow, so that means he transfers 200 joule of energy to that wheelbarrow. All right, so let's have a look at a few different types of energy. So first of all, kinetic energy. Alright, so kinetic energy is the energy, kinetic energy is something has when it's in motion. So something's moving, it has kinetic energy. So in your notes there, they're the two missing words. Alright, so if we then consider this thing here, that's an object, it's got mass m. Originally it stopped, it gets acted upon by a force, F Newton, and it moves from where it is there up to here. Alright, something like that. And it's moved a distance d. So that's the case. There's been a force acting on it over a distance, and so as we know, work has been done. So work equals the energy gain, and in this case, because it was stopped and then it's moving, it's kinetic energy. Now in this case it's the final kinetic energy, but kinetic energy nonetheless. Alright, so I've got final in the notes there. So the final kinetic energy, in this case it is, would be equal to the work done, which is, work of course is force times distance, Fx. Now force is of course mass times acceleration, so it's max, and let's call that equation number 1. Alright, now if we grab hold of constant acceleration formula, it says v squared equals u squared plus 2ax, and what we can do then is we can get an expression by rearranging this for a. Now of course remember what I said up here, there's that x is that d, and the initial speed is, or velocity is 0. So v squared, so u equals 0, x equals d, if you like. And so then we go v squared equals 0 squared plus 2ad. Then when we rearrange that, well, first of all, v squared equals 2ad, divide both sides by by 2 and d. Then we get the acceleration is v squared on 2d. And that there is equation number 2. And so what I'm going to do is I'm going to substitute that into equation 1. Now equation 1 I didn't quite have right because the distance that it moves, in our example, we've called d. So what I'm going to do is equation 2 is going to go into there. So the work done, which is the final kinetic energy, so the final kinetic energy will be, well, we had mass times acceleration, which is v squared on 2d, times by d. And if you're looking at the notes on the website there, I've mucked up my symbols in a few places, but anyway, not to worry. The d's cancel, and so you have mv squared over 2, which now normally we see written as a half mv squared. So the kinetic energy, and the symbol that we can use is EK, E for energy, K for kinetic. So, as it says in your notes there, EK is a half mv squared. Alright, in fact, work done would, because work way back has said work is change in energy, so really it's the change in kinetic energy, which of course is the final kinetic energy. Take the initial kinetic energy. So, and the final, if the final velocity is v and the initially, so the work done is the change in the energy, which is a half mv squared, the final velocity, minus a half mu squared. Alright, let's have a look at a couple of examples. Alright, so most of the time really the one we're using is this one here. So let's look at a couple of examples and see what we get. Alright, straightforward one to start off with. Kinetic energy half mv squared, so that's half the mass there, 6. The speed that it's going is 3. So then we just put that in your calculator and you should get 27. And of course, joule is the unit of energy, just the same as it is work. Okay, next example. Body of mass 4 kilograms with speed of 3 meters per second accelerates to 6. What is the change in kinetic energy? Alright, so the change in the kinetic energy is its final, half times 4 times 6 squared, minus the initial, which is a half times 4 times 3 squared. Alright, that's using this one right here. So then when you work those out, you get 72 here, and you get 18 here. And so 72 minus 18 is 54 joule. So it changes by 54 joule. So the work done on the body, remember work is change in energy. So if the energy has changed, in this case it's kinetic, right? And the kinetic energy has changed by 54, then the work done is 54 joule. Alright, simple as that. Alright, so that's kinetic energy. So there's another type of energy called potential. And there's a few different categories or types of potential energy. All potential energy is energy that is stored. So anytime you have energy stored, you have potential energy. Now the symbol that we use for potential energy is the symbol U. So U, and then there'll be some sort of subscript telling you what sort of potential energy there it is, and there's lots of different types. Alright, batteries have potential energy, for example, in the chemicals in the batteries. Now the one that we're going to look at first is what we call elastic potential energy. Elastic potential energy, spring potential energy, however you want to term it. Alright, so springs, for example, or elastic bands, they can store energy when they're stretched or compressed. Okay, so just if you change from its natural length, so you change it from its natural length. Okay, elastic band, you can stretch elastic band. You got to do some work on it to stretch it, and then when you let it go, bang, it goes back. So what we can say then is that the energy stored, and this is in your notes, is equal to the potential energy of your spring. And of course that then is the work done, because remember that work is change in energy. So if we're going to stretch our spring, we're going to give it some potential energy by stretching it. We're going to do some work on it to stretch it. So the work done on the spring. Now, the thing with springs is, and Robert Hooke noticed this, he noticed that if you apply a little force, it stretches a little bit. If you apply a big force, it stretches more. And if you want to stretch it, or vice versa, stretch it a little bit, you need a little force, stretch it a lot, you need a bigger force. And so he said that the force was proportional to the distance that you move it. Now, of course, work is force times distance, so there's a relationship there. So Hooke actually came up with a law, F equals kx. Now, sometimes you see a negative there. All that negative means is that if you have this spring and you stretch it out here, you've stretched it this much, say that way in the positive direction. The spring itself is going to want to pull back the other way. So the force in the spring is in the opposite direction. I'll leave the negative out, but if you see one, that's what it means. Now this K here, that's a property of the spring. What it's made of, how tightly it's wound, etc., etc., etc. We call it the spring constant. And it is in newtons per metre. So how many newton it would when you stretch it per metre. So what you get is a graph. Alright, there's our graph. Fx, straight line, and from what we know from y equals mx plus c, goes through the origin. So the force would be the gradient times x, and the gradient, well, when we relate that to Hooke's law back here, F equals kx, from Hooke, the gradient, as it says there, is the spring constant. So now we've got a force that changes depending on how we do it. So we've got to do the potential energy of the spring, this is in your notes underneath that, is equal to the work done on it. Now, because the force is not constant, changes depending on how much it's stretched, we can't just use F times X for it. We have to, as you remember from earlier. Okay, we can't use, here we've got our force distance graph, and it says here we can't use F times X because the force is not constant. So on a force distance graph, we look at the area underneath the graph as being our thing, and so of course the area in there, because it's a triangle, half base times height, and so the base is x and the height is f, so the normal way we write it is a half fx. Now the other thing about it, because it's Hooke's law thing here, and Hooke said that f is equal to kx, we can substitute that in there. So then what we get then is that the work is a half, instead of force we put kx times x again, and so that's a half kx squared. So the potential energy, S for spring, is equal to half kx squared. Okay, so when we, it says here in your note, for it, so if we get a spring here and then we hang something on it and then we pull it down here and then let it go, this thing in the middle, it's going to bounce backwards and forwards. So what you're going to have there is some changes of energy. When it's moving, it's going to have some kinetic. When it's stretching the spring, it's going to have spring potential and so on. But your total energy in all that case would be the same. So the energy total is the energy kinetic plus the spring potential. All right, let's do a couple of examples. Here's the first example. It says here, find the potential energy of the spring when compressed 0.2 meters. So there's our 0.2 meters. So remember, our spring potential energy, half kx squared. Right, we'd have to find k, we'd have to find the gradient, which we could do, but remember that's energy. So the spring potential would be the work that's done on it. Which would be the area in this case. So it's a half times the base 0.2 times the height 4, and so you get 0.4 of a joule. Alright, next. Alright, this example, it says we've got a spring constant of 5 Newton per metre. What's the change in potential energy? It's compressed from 0 to 20 centimetres. Now don't forget, always in metres. So 100 centimetres in a metre means we've got 0.2 metres. Change in the potential energy, so spring potential, half kx squared. It's a horrible looking half there, isn't it? Let's fix that up. So that's a half times 5 times 0.2 squared. And when you put that in your calculator, you get 0.1 of a joule. So if compressed by 20 centimetres, the body's placed there and let go, what is the kinetic energy of zero compression? Alright, so we put there, we whack this thing here. And of course the natural length, of course, and so this is where we've got to. Our natural length here is there, and that distance in there is 20 centimetres, 0.2 of a metre. And then we let it go. Want that colour, I want this colour. We let it go, and it then stretches out, and our box on the end there, and so things moving. So we've got spring potential here. We've got spring potential as 0 there, and that spring potential here we worked out in part A, which is 0.1. And so now we've got some kinetic. So remembering back to the energy is neither created or destroyed, but converted to from one to another. So we've got now gone spring potential to kinetic, so 0.1 joule is its kinetic energy as it passes zero compression. Alright, we're nearly there. More type of energy to look at, and that is gravitational. Potential energy. Alright, UG. Gravitational. Alright, so we can, if we raise an object, or an object is raised, then you have energy stored. How do we know that? Because if we let it go, it moves. Then it gets some kinetic energy. So where's that energy come from? It comes from the stored energy when you raised it. So we raised it above the ground, and if we've got something, as we know, everything's got a weight force. So if we're going to raise this thing, we've got to do work against its weight force. So we've got to do work that way. Alright, here's a diagram. Alright, shows that. So we've got that mass there, and we've lifted it up, used to be here, we've lifted it up above the ground. So the gravitational potential energy is work done against gravity, or rather than it should be against the weight forces, a bit better. That's how I should be a bit more specific. Alright, so the work done against the weight force, and so of course work we know is Fx. The force we're talking about is the weight force, so that's mg, as we know, and the distance we're moving it is this distance here, which is h. And so that is simply the formula, mgh, alright, for gravitational potential energy. And of course it's in joule, because all energy is in joule. Alright, a couple of examples and then we're done and you can get on with the problem set. Very quick one here, a mass of 5 kilos is raised above the ground. What is its potential energy? So, gravitational potential energy, mgh, equals 5 times 9.8 is gravitation, times the height that we've moved it is 6. Put all of that in your calculator and you get 294 joule. Alright, example 2. Mass of 3 kilos is 7 metres above the ground. If released, what is its kinetic energy just before it hits the ground? Alright, 7 metres there. Alright, we let it go and it goes and it hits the ground. What speed is it in the instant before? So what have we got? What we've got is gravitational. It's a dodgy looking U. We've got gravitational potential energy being transferred to kinetic. Alright, so the gravitational potential energy, mgh, is 3 times 9.8 times 7. When you work that out, it's 205.8 joule. Now, as I said up here, that then goes to kinetic as it falls. And it doesn't all go at once, it goes gradually as it gets closer. But what we do know is the kinetic energy is a half mv squared. So 205.8 is equal to half times 3 times v squared. Times both sides by 2 and divide by 3 and you get 137.2 is the velocity squared, and then we square root that and you get that v equals 11.7 metres per second, and that's how fast it's going in the instant before it smashes into the ground. Okay, so there's the end of lesson 21. Some 3 types of energy there. So we've got kinetic energy and 2 potential energies, elastic and gravitational. As usual, if there's anything you didn't quite get through that, you need clarifying, make sure you do that. Also, there's some videos there on the website for you to have a look at. Right, problem set 21.